Now, pretty soon here, we're going to move on and start calculating some p-values in Microsoft Excel. But first, I need to complicate things a little bit so that we have the information we need to take on some more realistic examples during class. And the truth is, it's pretty rare to do a hypothesis test on a single value like we did in the last video, right? We measured one salamander, and we used a hypothesis test to determine whether or not that one salamander was statistically different from Meadville hellbenders, for example. A much more realistic case is where you have a bunch of measurements that you compare to a larger population or system, and you're curious about whether or not that group of measurements is statistically different or not. Okay? So in this example, on this video, what I've done is maybe in this case, I've driven up to Sagertown, and I found a bunch of salamanders that I think might represent a new kind of salamander, or at least a group of salamanders that's distinct from Meadville hellbenders. Okay, I measured one to be 9 centimeters long, and I've measured 3 more to be 11, 6, and 14 centimeters long, respectively. And in this case, my question is, do these group of measurements represent something that's statistically different from the population or the system that's described by a mean mu and a standard deviation sigma? Okay. So a logical place to start might be to calculate the average of this group of numbers, right? And so maybe what I do is I create a statistic here, x, and to indicate that it's the average of a group of measurements, I put a bar over the top of it. In this case, if I wanted to calculate the average of this group of measurements, I would say 9 plus 11 plus 6 plus 14. And because I've been really smart about choosing my numbers to be really easy to work with, if I divide by the number of values that I'm averaging, I'm going to end up with an average value of 10. Okay? And a logical step might be, okay, now I have one number to represent this group of measurements. Maybe I can carry out a hypothesis test to determine whether or not this value of 10 centimeters, whether or not this value of 10 centimeters is statistically different from my values that I would expect for Meadville hellbenders. Okay, but before we go too far down this road, what we need to do is realize that this number corresponds to the average of a group of measurements, right? But what these statistics correspond to are a bunch of individual measurements. Our mean describes the most likely measurement for a bunch of individual measurements, and our standard deviation represents the spread of individual measurements. And what we need to do is not compare apples to oranges, but to be able to compare a group average to statistics that represent group averages rather than individual measurements. So what I'm going to do here is I'm going to define a new mu, a new mean, but a mean that corresponds to the average value of group averages. Okay, so it's the mean of group averages rather than the mean of individual measurements. What I'm going to do is describe the standard deviation, not of individual measurements, but the standard deviation of group averages. Okay, cool. And one of the nice things is that these new statistics that describe our population of Meadville hellbenders are easily relatable to our statistics for individual measurements. For example, our mean of group measurements is just equal to our original mu. It's the same thing. It takes the same value as the mean of individual measurements. And that kind of makes sense intuitively if you think about it a little bit. Okay, how about the standard deviation of group averages? Okay, well, it turns out that if you average a bunch of values and compare those group averages to one another, the spread in those values is going to be less than the spread in individual measurements. And it turns out that the standard deviation of group averages is equal to the standard deviation of individual measurements divided by the square root of the number of measurements you make. So the standard deviation goes down when you're looking at the standard deviation of group averages. Okay, now what we can do is something similar to what we did before. Like before, we would calculate a z-score where we would find the difference between our measurement and the mean, and we would divide by the standard deviation to find the number of standard deviations away our measurement is. We're going to do the same thing in this case, except our measurement isn't going to be a single measurement, it's going to be a group average. And from that, we're going to subtract the mean of group averages, and we're going to divide by the standard deviation of group averages. Okay? And if we wanted to express this in terms of the mean and standard deviations of individual measurements, we can definitely do this. We still start out with the average of our group measurements, but from this we can subtract mu, because mu is equal to mu of the group averages, and we divide by sigma divided by the square root of n. Cool. So now we've got a z-score for groups. Okay, let's go ahead and plug in our numbers. Okay, our numbers are equal to an average of 10. From that, we subtract the mean of 20, and we're going to divide by the standard deviation of 5, which in the denominator is divided by the square root of 4, because in this case we have 4 measurements, so n is equal to 4. And if we were to punch in all of these numbers, we would end up with a z-score of -4. Okay, so this group of measurements is 4 standard deviations away from what we would expect if we were measuring Meadville-Hellbenders. Okay, this z-score is interpreted just like the z-scores that we calculated when we did the single value hypothesis test. What we could do is we could use Excel to calculate the p-score. And for the sake of this video, I'm just going to go ahead and tell you the p-value. And the p-value for a z-score of 4 or -4 is going to be equal to 0.000063. In other words, 0.0063%, which is way, 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 way below 5%, or 0.05. So what we know is that the probability of measuring a group of values that are more extreme than this group of values is really small, okay? And so what we can deduce is that our null hypothesis, which assumes that these measurements belong to the population of Meadville-Hellbenders, is false. The null hypothesis is false, which means that our group of measurements are statistically different than the population or system described by this mean and this standard deviation. And so it's quite possible that this group of measurements represents a different kind of salamander than the Meadville-Hellbender. Okay? The process that we just went through is called a z-test, and to distinguish it from the hypothesis test and the z-test that we went through in the last video, we're going to call this a z-test with groups. And in the next video, we'll look at how to carry out calculations like this and calculate a p-value with actual data sets in Microsoft Excel.